Can I ask before we begin, if you guys have watched, if you've watched HGL, EGL video yet, or if that's like, because if you haven't watched it, then for this to make any sense, I'm gonna have to do a little bit of discussion about what they are. Anybody just chime in?
Yeah, I'll be honest, I have not watched it yet.
Okay.
Yeah, me neither.
Okay. All right. Alvaro, don't that's enough. Two out of my 3 participants. So Alvaro, I don't need to hear from you, but by the way, one of these days I want to ask what our city kicks is. Perhaps now is not the time, but all right. So I'm going to do, so then what we'll do, let's see here. Where's my whiteboard? Share contents, whiteboard. All right. So what I'm going to do is I'm going to kind of talk about it. So these are all from homework 13. So like in the old homework, there's one called HGL, EGL, and usually HGL, EGL is kind of like, it's almost like an add-on to the energy equation. And so what these things stand for, I'm not going to go into a full teaching thing, but the hydraulic grade line and the energy grade line. And really, for some reason, they always do HGL, EGL when it should be EGL, HGL, because to me, the EGL is more fundamental. But so number 3 on that homework, it's got a drawing of, let's see, so it's got 2 drawings, and then it's got a little arrow on them. So the first drawing looks like this. We'll just do the first one and we'll talk about it, and then we'll do the second one. Okay, and so this is how I draw my turbines. It's not how they draw their turbine, but whatever. And then it's got a lower reservoir over here. Okay, and one of the things that I can guarantee on this is that this will show up on your final. It always does. I haven't made the final yet, but I can't really imagine not having this on there. Okay, so we've got water flowing between 2 reservoirs. The reservoir on the top has more head than the one on the left. And what I want you to think about as we stare at this thing is I want you to think about the energy equation, or really in a more simplified way, you could think about the Bernoulli, but I think energy is really the appropriate one here. So P on gamma plus Z plus, and I'm not going to worry about the alpha. Points are not really important here. B squared on 2G plus H from a pump equals P on gamma plus Z plus V squared on 2G plus HT plus the head loss. Okay, and so what we want to think about in general is I want to think of this as energy in. So I'm going to think about this as energy in instead of head. I mean, we measure it in terms of, a length, but it's just head, it's just energy. Okay, this is energy out. Energy out. And then the pumps and the turbines, this is another form of energy out right here, and energy out, but this is an energy loss. It's still an energy out, but I like mentally, I think about it a little bit differently. And this turbine, well, this is like, like we're actually stealing energy from the system. Like there's this is like, mechanical energy lost. But this is energy out due to humans, right? Due to us. So this is like anthropomorphic. So maybe we give it some eyeballs or something, and the same thing here, this is energy in. And again, that's not anthropomorphic, anthropogenic. Like we are making that happen. So I'll give it some eyeballs, like, we're doing it. Here's some nose and a mouth, whatever. Anyway, so at any point in this thing, I can plot all of these things. I can plot the Z, I can plot the V squared on 2G. And so what I want to do is I'm going to start right over here. And this is where my energy is coming in. This is the initial location for the energy in. So if I kind of like draw a little dotted line up here, it's entering the system right there. Okay, and if I wanted to draw the what's going on right there, well, how much energy do we have? Well, let's see. So we've got the P on gamma. Well, right there, P on gamma is 0. Okay, V squared on 2G right there is 0. The only thing I've got right there is elevation. So if I were to plot this, let's create a datum somewhere way down here. This is my datum. then what I could do is I could say, okay, well, at that point right there, this is my total energy. This is this whole thing right here. Okay, and basically it's Z at that point. No pressure, no V squared on 2G. Okay, I could pick another point if I wanted to. Like I could pick a point right here if I wanted to. And I think what you would notice right there is that, let's see, so if I were to measure these two, I still have no velocity because I'm pretty far from this opening here. I mean, obviously, as you get closer to this opening, maybe it's not obvious, but as you get closer, the velocity speeds up. But I still have no velocity. I've got a Z, which is going to here, okay, because that's my elevation. And then I've got some pressure. Well, what is the pressure right there? Well, the pressure right there is, if we were using, what do you call it, hydrostatic, well, we're going to start at the atmosphere, PATM, okay, and we're going to start up here. And I'm going to go down some bit, right? So I'm going to add gamma of the fluid times whatever this depth is, right? So I don't know what we call that. Let's call that H. Equals the pressure at our point. I don't know what I didn't call that point anything, but we'll just call that P. Okay, so if I rearrange this, well, pressure atmosphere is 0, right? And so if I rearrange this, I'm going to get P on gamma equals that depth right there, H. Which means that this H right here, that's P on gamma. Okay? So, and this will hold whether I put my point here or here or here or here or here, like any of these spots, right? What's going on is we're having a trade-off between pressure and depth, okay? But the total amount of energy, which is what this energy in is remaining the same, okay? And so this quantity right here, P on gamma plus Z plus V squared on 2G, this is EGL, EGL. Okay, that's the energy grade line. And so basically, at any one of these points, if I were to draw the total energy in head, it would add up to, at this point, right where this line is. Okay, we're not losing any energy. There's no reason for us to lose energy between, somewhere out, anywhere out here to here to here. Like there's no friction because nothing's moving, so we don't lose any energy. Now what's going to happen is, and as we move from that reservoir to, I could make all the same arguments for this reservoir over here, while the EGL, the energy grade line, the total energy has to be on this water surface here. So it's here. Now notice we have less energy on the left, on the right than we had on the left. Okay, and that's because we lost energy as we went from the, this location, which I'll call 1, to this location over here, which we'll call 2. Okay, and so where did we lose energy? Well, we lost energy in all the places where we lose energy. Okay, or potentially gained, but in this case, we don't have a pump, so there's no energy gain, due to people. Okay, so this person was not very nice to the energy of this flow. But we did lose energy. Okay, and where did we lose energy? We lost it due to a turbine right here. So this is an energy loss right here. Okay, and we lost it due to head loss. Now, head loss can always be split into 2 bits. We get head loss due to friction, and we get head loss due to head loss due to, this is due to the friction on the side of the pipes, and this is due to what we call the minor losses. So that's anytime anything disrupts the flow. Okay, and so we're going to lose energy right here. Okay, that's going to be a minor loss. We're going to lose it due to this valve right here. Okay, and that's just because something's changing in the pipe. Anytime something changes in the pipe, there's going to be a loss. Okay, and we're going to lose energy right here. So those are the places where we're definitely going to, those are the minor loss, or I guess, okay, so this is a turbine, this is minor, 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 and then we're going to have friction losses all along the pipe wall. Okay, so now you're going, okay, so how do we draw, so what I want to do is I want to draw this energy grade line, and I want to keep track of the energy going from the reservoir at 1 to the reservoir at 2. okay? And so what's gonna happen is, so this, let me draw it in like green or something because this black is a little bit ubiquitous. So we'll go here, and then, I mean, this is obviously an approximation, but we're gonna lose some energy here. So I'm just I'm gonna go down a little bit. Okay, now how much? Right now it's just qualitative, so we're not gonna quantify this, so let's not worry too much about that. But we're gonna lose a little energy right there. Okay, and I should note that we're gonna lose a little energy right here, so there'll be a little downtick here, and there's gonna be a little downtick here as well. Okay, I'm not putting them in place yet because we don't know exactly where they're gonna end up, but, and then all along this pipe, as we move along, right, there's gonna be a slow bleeding of our energy. We're just gonna lose energy, so it's gonna have a downward slope. Okay, we're just like slowly losing energy. We're gonna hit this turbine, and we'll, however much energy we lose to the turbine. Now, I don't know how much that is. It's hopefully bigger than for just one of these little valves or entrances or exits or whatever. But obviously, this is qualitative. So if I were grading this, all I would need to know is I would just need to see that you had a little downward line right here. And then we were going to go, so again, we're still moving along the pipe. So we're going to lose energy between the turbine and the valve. And then we're going to lose a little energy here. And then we're going to keep cruising along this way. Okay, again, we're losing energy. So the slopes of all these lines, let's call it A, B, and C, should all be the same. And the reason they're the same is because it's the same pipe with the same diameter. So we have the same velocity flowing through there. So even though I didn't do a good job of drawing it, what most of my students will do on a test is they'll say the slope of A equals the slope of B equals the slope of C. And that's a way to cover for, like, they're not very good drawers. Okay. So if you want to do that, that's fine. And sometimes, and there are definitely cases where they're not supposed to be the same. So sometimes people will say like MA is greater than MC is greater than MB if they want to say, like, if they just want to express what that relationship's supposed to be. So I'm gonna go ahead and erase this one because that's definitely not the case for this particular problem. And then we're gonna have a little drop right here of energy right there. And then we're gonna go here, okay? And so this is EGL, okay, the energy grade line. Okay, so I don't really like my drawing because I do prefer my slopes to be better drawn than this. So I'm gonna fix it a little bit, but it's not, right now it's not super critical. Maybe that's better. It's a little better. Anyway, the curse of being perfectionist. Okay, so then the last little bit here, and I do want to make this point right here real quick. This loss from an exit is V squared on 2G. Okay, so just be aware of that. So if it's an exit into an infinitely large reservoir, that little loss right there is V squared on 2G. And that's going to be important in a second. Okay, so then what we do here, and on this problem, it's a little bit trivial, but that's okay, is that, so I guess I'll put over here, EGL basically is the line. I guess it's EGL as a function of X, right? Because it depends on where in this system you are, is just P on gamma plus Z plus V squared onto G. Okay, that's the EGL. HGL of X, and this is the hydraulic grade line, and that's P on gamma plus Z. Okay, and I think I think it's important to know what those are, and it's important in some ways to wrap yourself up into those a little bit. But what I want to make, what's most important to me is that the difference between these two is just V squared on 2G. So what you want to do here, especially if you can identify V squared on 2G. Now this pipe is constant diameter, so it's the same V squared on 2G everywhere. So this little thing right here, that's the V squared on 2G. So the difference between the HGL and the EGL is this amount right here, this same amount through this entire thing, okay? So the lines are always going to be this distance apart, okay? The same distance apart. Again, I'll have people, label these distances, like they might call this distance, I don't know, 4 or something, and this distance 5, and this distance 3, and they'll make a note that they're the same everywhere. You know, again, imagining I could draw it perfectly and it would look something like that. Okay. And that's how you draw an EGL and HGL. Now, the cool thing is there's a lot of information in that we hadn't thought about before. And that's like my favorite thing about these is that when it's all said and done, okay, this right here, that's the V squared on 2G. Okay, notice also that the HGL and the EGL are identical over here. They're going over the exact same area lines. Okay, and the reason they do that is because there's no velocity out there. Okay, so there's no velocity, then there's no velocity head, then they cover the exact same, territory. The other thing this shows me, so where's the Z for this flow? Well, the Z for this flow is right here, and the Z 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 is in all these places. So that's the Z. Okay, so if this is V squared on 2G right here, and here, and here, and here, and this is Z, okay, then what's left is P on gamma. Okay, what's a good color for that? I don't know. Here we go, red. So P on gamma is here. So what's cool here, and this is something we hadn't really thought about very much, okay, is that the pressure is decreasing all along this pipe. Okay, and every time we have a head loss or a turbine or anything like that, in a system with a constant velocity, with a constant diameter pipe, every time we have a turbine or a head loss or whatever, it's affecting the pressure. The velocity is not affected, and the elevation is not affected. Okay, so it's really the pressure that's being kind of whittled away at. So that's, I don't know, I think it's pretty cool. It's just not something I ever really thought about. Now, sometimes people will say, well, how does that make sense? Like, how is it that losing energy to a turbine or losing energy to a head loss does not affect the velocity? Because it seems like, if we take more energy out, we should have, less velocity. And it's true that what will happen is, let's imagine that the turbine, we put in a more efficient turbine or whatever, we take out more energy due to the turbine. Okay, so let me see, maybe I'll do this in black. Maybe I can draw this on top. So if we have, let's suppose we still have this loss here, well, whatever. I could draw an alternate energy grade line. That would look like this. And now we're gonna lose a bunch to do this turbine. Because the thing is, we still have to end up here, and we still have to start here. Okay, so I have this huge loss here. And then I'm gonna go here, I'm almost flat, because it's, well, maybe that's not flat enough, I don't know, let's see. Let me delete that. Let me lose more energy here. Let's come back this way. So what happens here is if I have a turbine that takes a lot more energy, so this distance right here, that's the head due to the turbine. Okay, if I have a system where the turbine takes a ton of energy, what's going to happen is, basically there's a lot less energy in the system, and so there's less velocity head. So now the V squared on 2G might look like this, but it's still constant throughout the system. Okay, and the reason it's constant is because this pipe has the same diameter everywhere. Okay, so it's constant throughout the system. So like this little drop or this drop here due to that valve or whatever, it doesn't affect we still have the same velocity throughout the system, but once it's adjusted, we'll have the same throughout everything, but the adjustment will end up with less total energy for that. And one of the reasons for that is that the energy loss here, due to the pipe, that is F L on D V squared on 2G. So it depends on the velocity head. So if more energy is lost here, we can't lose as much along these pipes. And the only way the pipes can really adjust is by going slower. So the pipe, it just slows down. Okay, I'm gonna do another one of these because the first time you see this, it's kind of like, wow, this is like an awful lot. But conceptually, like, it's more important to me that you see this conceptually, like what's going on, what we care about, what we're doing. Then, I mean, obviously I want you to be able to draw these. but the concept is the hardest thing. People get very confused dealing with these two things. So let's go ahead and I'm going to clear this one. I'm going to do the next one, unless anybody wants to interrupt me because they have another question. Let's see. All right, so I'm going to clear all drawings. And again, I'm going to write over here the formulas real quick. EGL equals B on gamma plus Z plus V squared onto G. And HGL equals P on gamma plus Z. All right, so in this one, it's almost the exact same drawing, which is a little bit annoying. I really love this question. And it's got a pipe and it's got a pump. The nice thing about pumps is when you see a pump, the water, well, the not so nice thing in some ways is that with a pump, the water can go in either direction. I'm going to give us some space between the valve. By the way, this little drawing of a valve, if you can't see it, think of it as like a faucet. That's how I always imagine it. I mean, a faucet is a valve. You know, so you put your hand up here and you just spin it. And then we've got this. Okay, and so we've got like, you know, a water surface here and a water surface here. Now, the annoying thing about a pump, as I said, is that in this case, the water could go in either direction. With the turbine, the water had to go from left to right because it has to flow from high energy to low energy, assuming there's no input. But in this case, we have an input. The input is the pump. So we could pump water uphill, or uphead, but we cannot turbine water uphead, right? So whatever that means. So P on gamma plus Z plus V squared onto G. Again, I'm not going to worry about the alpha here. HP equals P on gamma plus Z plus V squared onto G plus HT plus head loss. Okay, and again, we want to remember this head loss gets split into head loss due to friction and head loss due to minor losses. Okay, now the last little bit of this thing that they gave me, which is on the drawing, is that the flow is going this way. And that's important to know because otherwise the drawing is going to be totally wrong. Okay, so we're just going to go ahead and do something real quick. We're going to get rid of this turbine term because we don't have a turbine. And you know, that's just a waste of our brain power to consider the turbine. Okay, so same thing as last time. I'll draw like a little datum down here. I don't think I dotted my datum last time, but so here's my datum. Okay, and whenever you have a reservoir, let's see what I don't remember the colors I did last time, but here this is going to be my EGL. So EGLs will be, this EGL will be green. Okay, so this is the EGL. Whenever you have a reservoir, the EGL is at the reservoir surface because there's no V squared on 2G and the Z goes all the way up to the surface. Okay, and so then we're going to be here. And that's really important to know because when drawing these things, you need to know where you're going. Okay, I'm also going to show you a little trick that I do when drawing these because I already made an error for drawing this. Not an error, but something that's going to make it way more difficult. And sorry, you know, motorcycles. Anyway, so then the other thing that I like to do then is I'm going to be going from reservoir 1 to reservoir 2 is I like to think about losses. So I say, okay, well, we're going to lose energy here. We're going to lose energy here. We're going to gain energy at the pump. So maybe we'll put a different color there. And we're going to gain energy there. And we're going to lose energy here. So those are all the minor losses. And then we're going to have the friction losses. Maybe I'll make those a different color here, you know, all along the sides of the pipes. Okay. Now my expectation, of course, is that you'll be able to see that, you know, as you go, you know, as you do these, you know, you won't have to like circle them every time, but it's not the end of the world if you have to. So what we're going to do is, so as I go from 1, I'm going to travel to the left. I'm going to hit the end of the reservoir and I'm going to lose a little energy. Okay, again, this is just qualitative, so we're not really worried about how much. I just want to see a downward tick. Now, I hope you won't go crazy and draw it like that. Okay, that's just, I mean, it's not wrong if it's just qualitative, but it's a little silly. You know, just draw enough that I can clearly see that you're losing energy. Okay, and then we're going to start going downwards. okay, at some slope. Okay, now I went pretty steep here. Is that possible? Yes, it's possible. Okay, you can have your line go below your pipe. Okay, and that's kind of an important idea. And it, that's just what happens. Okay, so we're losing energy all along there. Now I'm going to hit this valve. When I hit the valve, I'm going to lose a little energy. Again, how much? Depends on the valve. Some valves are very, well done, and you don't lose a lot of energy. Sometimes, like one of them that's, I think it's in your textbook. There's a globe valve that loses 10 times your velocity head, which that kind of stinks, right? You don't really want to lose 10 times your velocity head. Anyway, so then we go down a little bit, and then we're going to keep going down. This pipe, if I had drawn it correctly, was the same diameter the whole way through. So we're going to continue to lose energy at the same rate. Okay, so now we've got really, really low. We're really, really down there. Okay, and we'll talk about what that means in a second. And it won't necessarily be obvious to you yet. But then, okay, we get this pump. And so the pump is going to add energy to this system. So we're going to go like this, and we're just going to add. Now we add it like it all goes on at one point. Obviously, this is all happening within the pump, but we're not going to worry about that. So we're going to go up. Now here's the problem, right? This is the problem with my drawing, is I can't go high enough here. So what I do, and I do this on tests, is I erase my water surface, because my water surface is annoying. Because it's in the wrong spot, and I didn't know where it needed to be, but I know that I drew it in the wrong spot. So I erase it, take some artistic, license. Okay, and basically I'm going to try to keep this slope as best I can. I've got my ruler out in hopes that I can kind of more or less approximate this. Okay, so there we go. That's more or less the same slope as the other lines. Okay, and now I'm going to redraw my water surface. But first, I've got an exit. So I'm going to lose v squared on 2g right here. And that will tell me where my water surface goes, which is going to be right here. Ideally, your water surface was drawn better, and you didn't have to resort to such measures. But that's okay. So this is my energy grade line. Okay, so now we'll do the HGL. I don't remember what color I did last time. I guess we'll just do blue. HGL. Okay, and all we need to know, so like right here, this is v squared on 2g. Now be very careful, that's v squared on 2g right here. That's not v squared on 2g over here necessarily. In this problem it is, because we've got a constant diameter pipe. Okay, we'll do one that's not a constant diameter pipe in a second, and we'll kind of talk through it a little bit. Just be very careful with that. So this v squared on 2g, so that means everywhere my HGL is below my EGL by that amount. Okay, so I'm just going to go like this. By the way, when you do this on a test, I usually have you do a solid line and a dashed line for the two so that I can distinguish. It's really just to let me know that you know which is which. It also makes a nicer drawing, but So then we're just going to keep v squared on 2g constant through the whole thing, because we have a constant diameter pipe. Like that. And it looks like I went a little overboard right there. Anyway, so that's it. We just did it. Okay, so this is HGL. Okay, now we're going to assume that this distance is the same everywhere. Obviously, I did the best I could. It's not perfect. And so usually if it changes, you want to make that change pretty dramatic so that your grader can see. So now I'm going to think about this quantity right here. I'm going to think about all of these things. Okay, so I'm going to erase all this stuff. Okay, and really to me, at least at this stage of your education, the most important thing here is that you're just thinking about this. Okay. Yeah, because we do all this work with these equations, but we never think about usually what's going on between point 1 and point 2. Okay, and this is all of that. This is what's going on. And so, anyway, obviously over in the reservoir, it depends on where the point is that you're looking at. you know, what's the pressure, what's the Z, right? Like if this is our point, this is the Z, and this is the P on, this is the pressure head, right? So that's if we're over there. Okay, but really, like what we're concerned about really is in this pipe. And in this pipe, here's my Z, or my Z, excuse me. I don't like to say Z. It's too confusing. So here's Z. And Z in this problem does not change. It does in other problems, but Z is up here. Okay. All right. Now we got, and then we've got V squared on 2G is this. Okay, and it's the same everywhere. So then the last thing we need is we got pressure, right? We got P on gamma. And I don't know a good color. We'll do red here. So P on gamma goes from the Z to the HGL. So this is P on gamma. Okay, P on gamma. Okay, so notice, oh no, my computer is dying. Oh, nope, didn't die. Can y'all still hear me? Can I get a thumbs up? Just
Yeah, I hear you.
Okay, good. I just have a, well, y'all look funny now, but that's okay. If the computer dies, I'll undo my audio on my eye thing. And then you'll see the bottom of my beard instead of my entire face. Anyway, so this relationship right here, that P on gamma goes from Z to the HGL, continues over here. And so here's P on gamma right here. Here's P on gamma right here. Oh yeah, it's right here. And there's a point right here where P on gamma, where the pressure is 0, or atmospheric. And then it starts to be positive again right here. Okay, so it is between Z and the HGL. Okay, so now we're gonna tell a little story about this flow. Okay, so like right here, I'm gonna follow a streamline, more or less. Okay, so right here, our energy is all in terms of Z, right? So we're all Z right here, all Z, right here. Okay, we start to flow down. Okay, maybe there's a point like right here where it hasn't technically really started to move yet because we're still like far enough away from that opening. And so now we are Z plus P on gamma. Okay, we've got Z has gone down, P on gamma has gone up. So now we've got some pressure, okay, hydrostatic pressure, but we've lost elevation. Okay, now as we enter the pipe, okay, once we get like right here, maybe, let's start giving some points here. Once I get right here, okay, Z is constant. Okay, the pressure has now dropped. And we see that, we see that because V squared on 2G has gone up. Okay, so now we've got some velocity head. Now for the rest of this flow to the left, this is going to remain constant all the way across. The Z is going to remain constant all the way across. And you can see the only thing that's changing is the pressure. And so we're losing pressure. And so the pressure here was atmospheric. It's also atmospheric right here. Okay. And then it turns negative. And let's not be afraid of the negative. Okay. If P on gamma is less than 0, then that means that P is less than 0, which simply means that the pressure is less than the atmospheric pressure. That's all it means. Okay, so don't be scared. Okay, now it does mean on some level that you might say to yourself, okay, well, as long as it's positive, we don't worry about cavitation, right? Because it's definitely never going to happen. As soon as it starts going to negative, you start thinking maybe we want to check. Maybe check for cavitation. Okay, now I will ask you to do that probably on a test. And so one of the things I will ask you to do on this is I'll say, where is cavitation most likely? okay? And where cavitation is most likely is where the pressure is most negative. Sometimes there can be more than one correct answer here, but on this particular problem, it's where it's most negative, and it's most negative right here, right before the pump. Okay, so usually like in a problem statement, I'll say, tell me where you would check for cavitation, and you should put a star right here, okay, on the drawing, like, because this is where, where cavitation is most likely right here. Cavitation, most likely. Now, obviously, if you do the math and you discover that cavitation will happen right there, then you need to figure out where cavitation, where, how far back this way do the pressures drop low enough where you're like, okay, we need to worry about cavitation there. Okay, so that's just one thought. Okay, now notice all of a sudden we hit the pump and all of a sudden we're really pressurized, and and cavitation is no longer really a possibility. Okay, so what I will say about this, so that's kind of the story of this is, as we flow from here to here, is pressure dropping, pressure dropping, pressure dropping, pressure takes a hit, pressure gets to its lowest point, we hit the pump, super pressurized, but again, we immediately start losing pressure again, lose some right here, and then we lose our velocity head as we come out this way. Okay, and that's the story. What I will say is this is why when you're designing things, and you'll notice that you design things, like for example, if you were in California and you were trying to get water from Northern California to Southern California, and there's a mountain range in between. So you're like, okay, how do I get the water from one side to the other? Well, you're like, okay, we're going to pump it, obviously, but where do we put the pump? If you put the pump, let me draw this real quick. Let me just take some of this side over here. Come on, you can do it. Okay, so if you put the pump, temptation is to put it on top of the mountain. Okay, so if you do this, if you're like, okay, well, here's my pipe. There's a mountain right here that I can't drill through for whatever reason. Okay, I need the water to get to the other side of this mountain. Okay, so you're like, all right, so I'm gonna have the pipe go like this, and then I'm gonna have the pipe come back down. Okay, let's imagine I did a better job drawing. Okay, if I put the pump right here, okay, then this is what's gonna happen potentially. Now this is a mountain, so this is a lot of feet, right? So this could be 2,000, 5,000 feet, whatever. Southern California, they've got mountains that are 10,000 feet. Let's just imagine we've got 5,000 feet of head right here, or 5,000 feet, Z, right? So what's happens is we've got this water coming in, and its energy grade line is dropping. I suppose well, we need to have enough to get up there, but let's just imagine it's dropping and dropping and dropping and dropping and dropping, right? We're losing energy. We'll lose a little bit because of this thing, but I'm not worried about that right now. Let's see what happens. Oh yeah. So we're dropping due to the friction, and then we get this pump, and then we go up, and then that gives us enough energy to make it across. Okay, let me redraw this a little better. Okay, let's imagine that we're dropping, and then we pump up, and then we start losing energy again. Okay, this is the EGL. Okay, notice I could do the HGL, constant diameter pipe. This is the HGL. Okay, cruising along like that. Notice this is how negative our pressure is right here. This is P on gamma, and it's really, 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 really negative. Okay, so if we do that, the risk of cavitation becomes really, really, really large. So we don't design systems like this. What we do instead, exact same pump, exact same scenario, is we put the pump, we're gonna put the pump instead, we'll put the pump right here. Okay, there's no pump right here. So we're losing energy, and then we hit this little thing right here, and it pumps us up. Okay, so if I imagine this line is the same, like that. So it pumps us up and then we start losing energy again. But what happens is we never go, or at least we never go as negative, right? And if we're lucky, if we put the pumps in the right spots, we never have to have negative pressures at all, right? But right here, notice we've got, this is a positive pressure. This is a positive pressure, positive pressure, positive pressure. We always have positive pressure. So the risk of cavitation is gone. And all we've done is, but it's with the exact same pump. Because in these two things right here, HP and the HP are the same. It's almost just like a geometry problem. It's like, where do you want this to, pressurize? Well, we want it to pressurize on the bottom so we don't have a risk of cavitation. Last thing is, if I ask, then what you do is, you'll say, okay, well, you'll pick a point. Maybe it's this one. Maybe it's this one. Oh, let's see, maybe it's this one, it's one. Either one, or let's see, two, right? Because we're going from 1 to 2. You'll pick a point. Okay, do the energy equation from 1 to, let's call this to star, or star to 2, right? So either one of those. So you can either start here and go to here, or you can start here and go to here, and you'll do the energy equation. And what you'll solve for is the pressure at the star. Okay? And that pressure at the star, probably the way you solve for it, it's going to be a gauge pressure. So you'll need to convert that to an absolute pressure by adding the atmospheric pressure. And then you're just going to compare it to the number in the chart in the book. So there's a chart in the book for the vaporation, the equilibrium vapor pressure of water at a given temperature. And so you'll just compare those two. Hold on, I'm hearing weird noises. Let me make sure my dog's okay. I'll be back in a second. Yeah, that was definitely not what I wanted. I have a little plastic bin that I fill up with water so he can jump in it. He was eating it. Okay. Anyway, so this is the idea behind the HGL and the EGL. And so far, we've only had constant diameter pipes. They're not that much harder with a non-constant diameter, but it just takes a little bit of thinking, or a little bit more thinking. So anyway, any questions about this before I go to a different problem? Okay. Then I will, they're all drawings. Let me see if my computer hasn't, oh, you know what, it's Chrome, that's not really, oh no. Chrome, don't do it. You know what, I can just make one up. Yeah.
I can see you moving on one of your videos, but your main one that you're usually talking on is frozen.
Okay, can you all hear me again?
Yeah, I can hear you again.
Okay, cool. Sorry about that. Hope I didn't miss anything. My dream is always that, this is all teachers' dream, that like, something will happen, you have to walk out of the classroom or whatever, and your students will sit there and discuss the science and learn from each other. So
I tried to say something to you, but I guess you probably didn't hear me.
I saw your lips moving. Let me see here. All right, so 11:49. So we've got what, 25 minutes? Okay, I'm gonna do this one. This is one of my favorite types of problems. So this is number 2 from the HGL EGL homework. I like these because they really make you think. It's also like from a teaching standpoint, from an exam standpoint, like really easy to grade. So I hate to do things for that reason, but sometimes we make those decisions. So this is number 2 from homework 13, EGL, HGL. Okay, and I'm going to do as well as I can drawing this. And basically what it is, it's a drawing of an EGL and an HGL. And then it asks you to interpret what's going on. Okay, let's see here. And some of this, you're not, based on what we've already done, like if you had watched the video, you'd be ready to understand, but you may not be ready yet, but that's okay, because we're going to talk about it. I was so proud of that line. Okay, so that's the EGL. This would be better if I could do this all on my laptop in a functional way, so that we could I wouldn't have to show you this image. All right, so this is the HGL. I'll just write that in blue. Okay. All right, so the first question they ask when they draw this is, they give us, I didn't write this question. So this is B, this is C. So I am going to ask y'all to speak up. So far, I've heard Paul. I think Max let me know he was here. And for Alex, for Alvaro, I just got a cool Our City Kicks image. All right, so the first question it says is there any hydraulic machinery in the system? If so, where and what type? And so if it says, is there any hydraulic machinery, what they're asking is, are there any turbines or pumps? And any idea if we have turbines or pumps?
I would think we'd have a pump at A and C.
Okay,
it goes up.
How do you know that's going up though and not going down?
I guess that's true.
You're right, it is going up, but there is a good way to tell that it's going up.
It depends on the direction of flow, right?
Right. How can you tell which way it's flowing? Which direction are we losing energy in?
Oh, from the left to right.
Right. So you see how all the lines are sloping downwards to the right. So because we're losing energy as we go from left to right, then that's the direction that the flow is going. Okay, so like all of these right here are sloping downwards, and that's due to the friction on the walls of the pipes. Okay, so yeah, so those are pumps. Okay, good. And then it says, is the pump prior to A larger or smaller than that immediately after A? Any guesses?
And it looks like you tried to draw them the same, so I would think that it's the same.
Like
the same slope.
As far as the slope, I did not try to draw them the same, but there's a much more obvious clue than that. Okay, okay, so the slopes are a little bit different, but this is B squared on 2G right here. This is B squared on 2G right here. Okay, so B squared on 2G right here is large-ish, right? B squared on 2G right here is small-ish. I don't know if you can see where I'm doing it. I can't really write B squared on 2G right there. B squared on 2G is smallish. So we've got more velocity here. If we've got more velocity there, then that means we've got a smaller pipe. Okay, so this is a relatively smallish pipe. We'll just call it a small pipe. Okay, I mean, it's all relative in this case because this is entirely qualitative. Okay, and then it says, is there a free surface such as a reservoir in the system? If so, where?
Would it be on the right-hand side by E?
Yes. Right, and how do we know?
Because it's flat.
Well, it's flat, so that's one thing. So we're not losing any energy, but there's something else too. Okay, and that is that the difference between these two things is B squared on 2G. And so there is no difference between them. So anytime there's no difference between them, that means there's no velocity.
Okay.
Okay, so then this one, again, this is like, we haven't really talked about this, but is the pipe between B and C rougher or smoother than that between A and B? So we're comparing the pipe from here to that between here and here. Where do you think the pipe is rougher?
Between B and C?
Right. Why?
Because the slope is steeper, so it's losing more to friction.
Yeah, because we're losing more to friction, right? So B to C, this is a rough pipe. Okay, if I'd drawn it 100% correctly, like what I was going for, because I think this is a little bit counterintuitive in some ways, is that V squared on 2G is still the same here, regardless, and that's just because of conservation of mass, right? If the pipe has the same cross-sectional area, then what goes in here and what leaves has to be the same, but but it doesn't mean that we won't lose more energy. So we're losing more energy in the rougher pipe. Okay. Okay. Which of the following is most likely to be located between D and E? Now you had to know that D and E was coming up. And you have to know that this little weird thing at B is coming up, right? Because those are the weird things in this one. So which of the following is most likely to be located between D and E? A gradual contraction, an abrupt contraction, a gradual expansion, or an abrupt expansion? And by gradual and abrupt, by the way, what they mean is if we were talking about an expansion, we'd be talking about something that looked like, so this would be an abrupt expansion. A gradual expansion would just be something that kind of did that. Okay, and then for contraction, it would be the opposite. You know, it would look like that would be abrupt, and this would be gradual. You know, so hopefully you can see that in this case, this is definitely gradual, whatever it is. It's definitely gradual. We don't have any, there's no sharpness to that blue line or to the red line. I mean, the black line, there's no sharpness. So it's going to be gradual. So it's not going to be any of these abrupt things. But then the question is expansion or contraction?
I would think contraction because the V squared over 2G is getting larger. So the
Right.
shape is getting smaller.
Right. So this is getting bigger. Okay. So V squared on 2G gets getting bigger and bigger and bigger. So it's contracting. And then it contracts essentially into this reservoir. So if I were to draw a picture of it, it's probably like, well, this is right in the way. But if I were to align it more or less, it would be kind of like doing one of these numbers. And then it hits a reservoir. You know, or whatever.
So this question was given, like asking us what happened at different points, but would we be given one of these and then asked to draw what it looks like, or no?
No,
Or just
so
tell you what happens.
So this one, this is the initial drawing was given, and I'm just reading to you the questions A, B, C, D, E, and F. So that's a possibility. If you look at the old test, I think I might even ask this exact question on an old test at some point. But no, I mean, to draw the actual system from that would be more than I would ask. I would not ask you to draw this, for example. Okay. Now, the last question that the last one that I gave you, the warm up to this one, I could ask you to draw the HGL, EGL for that one. In fact, I think I put that one on a test too. There's only so many things you can do in HGL, EGLs. Once you've seen a few, you'll go, oh, okay. When that one pops up, that's like, if you do a few, you'll go, okay, these are my free 10 points, you know, or maybe it's not 10, like maybe you'll get 8 out of the 10 because you do something a little bit wrong. You have careless error. These things happen, you know? So,
so we'll be asked to go from a diagram to an HGL, EGL, but not from a HGL, EGL to a diagram.
Right. Now, in this case, I might have a diagram and ask you questions about the system like we're doing right now, but I don't need you to draw this to draw it. I'm just kind of doing this as a, you know, to kind of picture what's going on here. Notice again that as I was talking about earlier, the HGL always comes right in to the surface. So it comes into right there. That's one of the things I check for, because your head loss right here, head loss due to the exit is always equal to V squared on 2G. Okay, so it always kind of ties into this point right here. And if you wanted to know, because I was just thinking as I was drawing this, like, why would you ever do this? Like, why would you ever create this? Like, why would you ever have a contraction going into a reservoir? Can you think of a reason why you might want to do that? I can think of one reason. And it might be, you know, so suppose this is a lake or something, and you got wind patterns, you got all these things going on. What you want is velocity here to remove any debris that might clog your system. So if you contract it, you know, you might be able to create a system where this does not get clogged. That would be my only real guess why you might want to do this. The other thing to note here is that as the velocity head increases, notice also the rate at which we lose energy increases. Okay, so this line gets steeper because we're losing energy at a faster rate. Okay, and that's because the head loss due to friction is FL on D V squared on 2G, and it's highly a function of the velocity head. So the more velocity head you have, the more energy loss you will have due to that friction. And if we wanted to make it per unit length, we would divide by length and we make it like this. So this would be the head loss. So this would be the head loss per unit length right here. And we multiply that by the length. Okay, so this is essentially the slope of that line. Okay, so then the last bit of this, and my computer has died on me again. I should probably just restart it right now. But the last bit of this is what's going on at B. Any ideas?
Is that a contraction in the pipe?
Okay, that's the right idea. And why do you say contraction?
Because it gets faster and then it gets slower again.
Right. So it's a contraction and then a re-expansion, right? So the way I think of this, whenever I see this problem, is what I think is probably going on is they probably have a pipe. They have a smooth pipe, and then they've got a rough pipe, right? So maybe I'll draw that kind of rough. And then they wanted to like attach them. And they're like, what do we have to attach it? Well, the only thing I've got is this thing that when it attaches, it takes up a certain amount of the space of the, it blocks a certain amount of the flow. So we get this so we get a real big increase in B squared on 2G, but just right in here. And then it goes back to being the same B squared on 2G over here as it was over there because conservation of mass. But yeah, I can't remember what the options were for this, but that's what they wanted you to kind of get at, was that there was a gradual, expansion, a contraction and followed by an expansion. So yeah, that's it. So I apologize. I'm restarting my computer. So I need to get another problem. How much time we have? We got 10 minutes. Okay. So let's see. I think on the next time we do one of these, which will be, I guess, next Tuesday or whatever, we'll probably do a full energy problem, and we'll put numbers to all of these things to make a really beautiful diagram here. But hold on, give me a second. I got to get back to Moodle here. Because what I also like to do, and I'm not alone on this, I think a lot of teachers of this like to do, is combine this with an energy equation problem. I mean, it's a natural combination. Let's see if I can get an energy equation, energy with minor losses. See if I can just find one that'll work. Problem is, like, the problems get a little bit repetitive. Let's see here. Oh yeah, I love this one. Okay, so I'm gonna go with homework 14, and this is energy with friction losses. And I have a problem that basically was given to me in one form, and then I just kept doctoring it to make it like more and more interesting. And of course, the diagram still aggravates me because it looks sloped, but I can't fix that for some reason. All right, so this is homework 14, number 2. Okay, so this looks like this. It's a reservoir over here. It tells you that it's water. Oh, well, you know what? Let's give ourselves some space. So when doing these things, also, always a good idea to give yourself some space. So you want to have your pipe. If you're expecting negative pressures, you want to have your pipe like in the middle of the screen. If you think it's mostly going to be positive, then you want to go down low in the screen. Okay, so there's a long pipe here. Okay, and we're going to pretend that I'm drawing straight lines. Okay, so it's a constant diameter, and then it's going to drop down like this. It's going to go like this, and now we've got a reservoir down here. Oh man. Okay, so let's erase that. And we've got a reservoir up here. And again, I like to keep, I like to be able to erase my reservoirs in case my lines get ugly. Okay, so this one right here, this is an elevation. There's an elevation over here. This one is an elevation 100 feet. This one is elevation question mark. So we'll probably solve this one in class all the way. But I want to draw the HGL EGL first. And I just want to talk about this one. And what I want to do before I draw it is ask if you guys can tell where cavitation is going to be most likely. before I draw it, which would be a really nice piece of intuition if you could do it. But not necessarily expecting it.
Is it right before, right at that bend?
It is right
Because
at
then
that time.
Because
And why?
it's going down, and then that's before the pipe actually starts to go down also. So it's
Right.
where it would be the most negative before the pipe starts to go down also.
Right. And so the nice thing, the other thing is, yeah, that's exactly right. So right here is where we're going to expect it. Okay. And it's exactly what you said. Basically, between reservoir 1 and reservoir 2, we're just going to lose energy the whole way. But the energy does not, unlike the other one where I drew it all flat, this one is not flat. And so since we're not flat, there's going to be a trade-off between elevation and pressure. And so just like in any hydrostatic fluid, when you go down in the fluid, your pressure tends to increase. So as you go from the star to, I don't know what we want to call this point, like this point right here, as we go from there, yeah, we're losing energy, but we're also losing elevation. And if we lose elevation, that will trade off by gaining pressure. Okay, and so let's just go ahead and draw it here. So it's just remembering it's P on gamma plus Z plus V squared on 2G. And again, like right now, we don't even have to think about that. We just have to think about energy and what's going to happen with energy. And so we're going to like cruise along here, and then we're going to lose energy here. There'll be a little minor loss here, a little minor loss here, and a minor loss here. Okay, I think by the time I assign this problem, you won't necessarily know how to deal with those minor losses, at least quantitatively. But we can draw like, oh, we get a little loss right here. All right, and I know I'm going to end up here on the far end. So I'm going to go up my V squared. I like to work this thing from both ends. So I'm going to go up my V squared on 2G here. Okay, and then what I'll usually do kind of is, let's do this in like a green line. So draw a line like this, and that just helps me with my sketch. Okay, and the reason is because I say to myself, okay, I'm going to need to be a little bit above that line because I'm going to have these two losses. So basically, I'm going to go like this. And then I'm going to have a loss. So I'm going to drop down right here. And then, well, let me undo that. I went a little bit too far. It's also easy to just erase your free surfaces, and then we'll try to keep the same slope. Oh, I missed it. Try to keep the same slope until we lose again. And then we'll try to keep the same slope here. Okay, and as I've drawn it here, it doesn't look like cavitation is very likely because we have positive pressure everywhere. Okay, I think based on the problem, I mean, and it all really depends on things, right? Like, so if this pipe is really, really narrow, or it's really, really frictional, if friction is high, then the slope of that line, the slope that you lose energy will be much higher. And the odds of going negative by this star are going to be much, much more likely. So with this drawing, the way I've drawn it right here, it's not even really all that clear that this is the spot. But when we start trying to keep track of things, so if I draw a datum down here, come on. If I draw my datum right here, and I say, well, here's my Z. Again, we're not really concerned about the reservoirs all that much, but here's my Z, right? And I don't need to draw it everywhere. But then my Z starts to shrink a lot. Okay, now we still can't really get at this because, well, I haven't drawn the, we don't need that guideline anymore, because I haven't drawn the V squared on 2G, but I'll go ahead and do that. We'll do that in green. So V squared on 2G, so we're going to go down by this amount right here. It's a constant diameter pipe, so it's going to be, as best I can draw it. Again, not perfect. I understand you all are not artists. Okay, but it is very helpful to use a straight edge and required. So, all right, so now we've got V squared on 2G, that's up here. Like that. So now if I wanted the pressure head, we do that in red. And so we see, okay, the pressure, we're just slowly losing pressure as we move down this thing. Okay, we're losing pressure, we're losing pressure. And here's the pressure at the star. It's right here, it's right before that bend. So actually it might be worse right after the bend, you know, but right after the bend, we're going downwards, and notice the pressure is increasing. All right, so where is it the worst? It's the worst right here. Okay, so that's why the star ends up being where it is. Okay, and we could, in some ways, we could think of that as being the pressure here, you know, kind of doing its thing, you know. But yeah, so as the fluid is flowing this way, it's flowing against the pressure gradient, but gravity is helping it out. So that's kind of the trade-off: elevation versus pressure. So yeah, so that's really it, you know. And this is the HGL right here, and this is the EGL, you know. And I think as long as you draw them with the EGL first, and you're just thinking about energy losses, and then you draw the HGL, and when you draw the HGL, the only thing you think about is the velocity head, then this makes sense. A lot of people try to draw them at the same time, and that's a disaster, in my experience. So, oh yeah, this is obviously supposed to be flat. So, you know, imagine I didn't draw it like that. Anyway, so we're about the end. So, any questions? You guys still there? You are still there. Okay. I can't see my screen anymore. Well, if no questions, then I will see you guys Tuesday. And I just got my COVID shot, so there is a small chance that my second COVID shot. So there's a small chance that office hours this afternoon won't happen, or that I'll be like zonked on the couch while while Zoom is open. But let's hope that I do better than that. So anyway, so I hope you guys are having a good day, and that's it. So yeah.
All right, thank you. Have a good one.
All right. Thanks, Paul.
Thank you.
Thanks, Max. Thanks, Alvaro. See you next time.
All right, take care.
Easy. Bye.